Morning to everyone. So our today's lead code question is 761, that is a special binary string. So in this question we are given a string s and it is a special binary string. So what is a special binary string? So for a string to be special, it has two conditions. That is, the first condition is number of zeros is equal to the number of ones in the whole string, right? And every prefix of the binary string, every prefix of the binary string has at least many ones as zeros. What it says, that in every prefix the number of ones is greater than or equal to number of zeros, right? The second condition is saying that the number of ones is greater than equal to the number of zeros in every prefix of the string s. Okay. And what a move consists of choosing two consecutive non-empty special substrings of s. So we can choose two substrings of s in the special substring s, and we can swap them, we can swap their positions, right? And at the end, what we have to do is we have to return the lexicographically largest resulting string possible after applying the mentioned operation. So let's see some examples. So here the first example that is given to us is 110110000. So see, uh, the number of zeros is 4 and number of ones is also 4 in the whole string. And if you take any prefix, let's say this prefix, the number of ones is 2, number of zeros is 1. You can take even this prefix, the number of ones is always either greater than or equal to the number of zeros. So these are the two conditions for this string to be special, right? So what we have to do is we can take any two substring, we can swap their positions, and at the end we have to return the largest, lexicographically largest. So lexicographically largest means maximum ones in the beginning of the string. So if you'll see, if we take this string and this string, these are also special strings, and we swap those twos, then we get 111001000. So this is the largest lexicographically possible substring string that we can get from this string s. Next, let's see the second example. So here the string is of length 2 only, so that will be the answer. So if you'll see, s dot length can be up to 50, right? So what are the possible complexities? So we can use recursion with exponential exponential time complexity, and we can use any big of n key power any cube 5 anything, right? Big of n. So we can use all the possible time complexities. And s of I string is either consist of zeros one, and s is a special binary string. So let's see the approach and the thinking process. So in the definition we are given that the total number of 1 is equal to the total number of zeros, and every prefix has, that is the number of 1 greater than or equal to number of zeros. These are the two things that we are given. So if we see this definition, this definition is exactly pointing to the valid parenthesis string. If we map 1 as open bracket and 0 as close bracket, so the number of open brackets is equal to the number of close brackets, and at any point the number of open brackets is greater than or equal to the number of close brackets. So it is pointing to the valid parenthesis problem, right? Okay. And one more thing, what does one move really allows us? So in one move we can take two special substring, consecutive special substrings and swap them, right? We can swap those two, right? So suppose s is equal to a plus b and then the rest part. So we can swap a and b with each other, where a and b are special substrings. So we can reorder special blocks, but only if they are already sitting next to each other. So suppose these are A and B. So we can reorder them only if they are next to each other, right? Because in the question it is given that we can swap only consecutive blocks. So if the whole string can be decomposed into consecutive special blocks, right? Then by repeated adjacent swaps, we can permute them in any order. So let me explain you this point, because this point is very crucial, or and we can say important point for our approach. Let's say we have decomposed our string s into four different blocks, or we can say four different special substrings, right? Suppose I want D to come at the first position. So is it possible for me to bring D at the first position? Yes, we can do. First what I do is I'll swap C and D. Then it will be A B D C. Then I'll swap B and D, B D. Then it becomes A D A D B C. Then A and D. Then D A B C. So see, now I get the string as DABC. So we can so in this statement it is given that we can permute them means these special substring blocks in any order, right? Keep this thing in mind, right? Because it will be helping us to formulate our approach properly. Okay, next, suppose I want that B comes at second place. So what I do is I'll swap A and B. Then this become DB AC. Now I want C comes at third place, so DBCA, right? So if you have noticed, we can bring these blocks at any position we want, right? So with this, our entire problem has become a new problem, that is, find the building blocks that can be swapped freely, as I have shown you above, and then sort them to maximize lexicographical order, right? So in above blocks we get four different blocks, right? A B C D. So suppose D is a block having the largest lexicographical string, so we have taken it to the first position. Then I think we have taken B. So isn't it like sorting these blocks? Isn't it like sorting these blocks based on the lexicographical order? Because we can freely change their positions, right? So if what we do is if we take the different blocks and then sort them on the lexicographical order, then again rejoin, then we get our final answer, right? This is the core concept of this approach. Next, what we see is what are the correct building blocks. So we have taken four blocks, but what are the correct one? So is it like taking all special strings? No, because if you take all special strings, then there will be overlapping and illegal to reorder, because overlapping will lead to problem. So we won't be taking all the special substrings. So what we do is we need a partition into consecutive special substrings, right? We partition the whole substring into consecutive special substrings. Now the thing is like how do we the natural partition. So in the question, we are given sorry, wait, let me go above. Yeah, so in the question what we are given is use the balance counter. What is balance? Balance means number of ones equal to number of zeros. So if we when we get 1 we increase the balance by 1, and when we get 0 we decrease the balance by 1, that is minus 1. That is representing 1 with 1 and 0 with minus 1. So what we do is we scan left to right, and 1 will increase the balance and 0 will decrease the balance, because the string is, and even the string is special, right? So balance never goes to negative. If you have noticed the second condition, that is the number of ones is greater than or equal to number of zeros in the prefix. So this will avoid the situation of balance becoming less than 0, right? At max, at least it can be 0 or greater than 0. And also, if a substring is balanced, so we know it will be starting from 1 only, and to maintain the count it will be ending with 0 and some inner part, right? So after this what we do is, whenever balance returns to 0, okay, when we get our balanced value, when we get our balanced value as 0, that means we completed a smallest top level balance segment which does not depend on the outside characters, right? What we are doing is we are uh, making a balance variable whose value is initially 0. So if we get a 1, we increase the balance by 1, and we get a 0, then we decrease the balance by 1. So when balance again becomes 0, that means we completed a top level balance segment. Okay, now we get a top level balance segment. So what we can do is we have suppose uniquely decompose our string s into different top level blocks b1, b2 and up to bk, right? As shown here, where each bi is a special and consecutive block. So these are the exact units that are swappable, means these are the units which we can swap at the outermost level. Now, as I already explained you, why sorting these blocks make the string lexicographically largest. So what does lexicographically largest means? Means maximizing first character, and if tie is there, then we will be maximizing second character and keep doing on, right? So if we can permute blocks freely, as I already explained you with the example A, B, C, D, we can uh, changing the position of the blocks anywhere we want. So that then what will be the best arrangement? So the best arrangement is putting the block with the largest lexicographical value first. So we have assumed that D was the largest lexicographical value at that time, so we have put D first, then B, then C and then A, right? So isn't it like sorting the blocks in descending order? Yes, it is like that only. So at the top level, what is our solution? Our solution is split the string into top level blocks. String the split string into top level blocks, then sort into descending order. After sorting, we get D, B, C, A, and then again join those. So this is our answer. So this is the at the top level, right? But there is one issue, and what is that? That each block has internal structure also, right? Which can also be further decomposed. So at top level, a special block always look like this. A special block always look like 1 plus some inner part and then 0. So if this inner part, we can decompose this inner part further also. And why this structure is guaranteed? Because in a special string, the first character must be 1, otherwise our prefix condition breaks, right? And when the blocks ends, the balance should hit 0, means the last character must be 0 only, right? So we get our outermost wrapper is 1 and 0, and then inside there is a inner string which is again a special string. So now what we do is, so the same operation that we were applying on the bigger substring can be applied on the inner part also, to make it to make the inner part as lexicographically largest, right? As inside this is also a special string, and it can be decomposed into consecutive special blocks also. So whatever we have done on the bigger block, we can do the same thing on the inner block, right? So if you see, so to maximize the whole string, what we do is we must maximize every inner special substring too, right? So if you see, isn't it giving us the feeling of recursion? See, what we have done is we have taken a block, then inside that block we have taken a inner string, and again doing the same thing that we have done on the block, we are doing the same thing on the inner block also. So that is pointing towards recursion. That is maximize inside each block and then sort blocks at current level. So if we see the full strategy, what is our full strategy? At every nesting level, what we do is at every level we divide the string into different blocks, consecutive special blocks, right? And then we recursively maximize each block. We maximize each block. What we do is, suppose we take block 1, so it is 1 plus inner part and then 0. Then we take this inner block, we maximize this inner block again, maximize each blocks inside. Same way we do for this block and this block. So at each level we divided the string into consecutive special blocks, then we maximize each blocks inside value, and then after maximizing we sort these blocks in descending order, and then we will be concatenating that and returning our answer. So let me show you an example to make you explain it more clearly, right? So suppose I have taken this string 10 sorry 110 1100. So we have taken this string. So let's see, at top level we will be trying to find the balance string. So initially 1 is there, so balance has become 1, then again 1 is there, so balance has become 2, 0, then we have to decrease balance by 1, so 2 to 1, again 1 is there, balance become 2, again 1, balance 3, 0, balance 2, 0, balance 1, 0, balance is 0. So we get balance equal to 0 at the end of this whole string. Okay, so in this string only one top level block is there, that is the whole string. So what we do is, now we must optimize the inner part of this string. So what is the inner part of the string? Starting from index second to the last index, that is 101100. So that's the inner part. So now what we do is we will be optimizing this part. So we'll be repeating again. In this string will be trying to find the top level blocks, right? So how will be finding top level blocks? Where balance equal to 0. So see, 1 balance is 1, then we get 0 balance is equal to 0. So we get our first block, that is 1 0. Then we start from here, balance is 1, then balance is 2, then again balance is 1, and here balance is 0. So we get our second block also, that is 1 1 0 0, right? Now what we do is, these are the inner blocks of that uh arey yaar. Yeah, these are the inner blocks of this whole block, right? So then what we do is we recursively maximize each each block also, right? But if you notice, this is also maximized and this is also maximized, so no need to further maximize these blocks. So what we do is, then we'll be sorting them in lexicographically descending order. So which one is lexicographically greater? 1 and 1 same, then we check the second character. 1 and 0, 1 is greater than 0, so this block is lexicographically bigger, right? So what we do is, at this level we'll be merging these two blocks. So now our earlier our inner block was 1 1, this is our inner block, but after sorting and merging it has become 1 1 0 0 1 0. So see, this second part is lexicographically greater than the first part. Now again what we do is wrap back. Wrap back means what was our initial string? Our initial string was 1 0 1 1 0 0 0. So we have taken the inner block, and then maximize it. So what we do is we replace this part with this part. So now our block has become 1 1 0 0 1 0 0. So this is our answer. So that's the lexicographically largest string possible. So if you'll see the code, it is a very small code, but the thing is that we are using recursion. So we are calling our main function again and again, right? So what we have done is at each level what we are doing, let's see that. So we have taken a vector to store all the blocks, and then balance equal to 0 and start equal to 0. Then we are iterating over the string. This is not the this is not always the bigger string, it can be the inner part also. So whatever part we get, we will be iterating over that part, and then we find balance, we increase balance. If s of I is equal to 1, then we increase balance by 1, else we decrease by -1. And if at any point we get balance equal to 0, then that means we get a block. So for that block, what we do is we take the inner part of the block. Inner part of the block. So inner part is, as we have already noticed, a block is 1 plus inner part plus 0. So we'll take this inner part, that is start plus 1, and whatever the length is, that is I minus start minus 1. Okay, so we take the inner part, and now we call the same function for the inner part, right? As I already explained you above, like how we'll be doing this. So we call the same function for inner part. Now this inner part will do the same recursion, and it will return as the best possible inner part, right? So then again what we do is we store our block with 1, then best inner part, and then 0. So we have replaced our inner part with best inner part. Now we get one of our block. Now then we'll be updating our start index of the block, that is I plus 1, that is the next block. Because this block, current block is from 0 to I, the next block will be from I plus 1 to some index k, right? And once we get all our blocks at this level, then we sort those blocks in the in descending order. And what will be our answer will be joining of these blocks, and at the end we'll be returning our answer. So this is a recursive function. So I hope I am able to explain you the whole approach. So if you like the solution, please make sure to like, share and subscribe the channel. Thank you.